Neural radiance field in the past few years has been a very hot technology in computer vision. In the last 3 to 4 years, there's been a lot of progress in computer vision, and especially for novel view rendering and 3D reconstruction from just images. This technique has done very well. So in this video, we're going to talk about everything related to neural radiance field, and I'm going to go into detail about how it works and how we can understand the math behind it, the science behind it. So stay tuned until the end. So guys, welcome back to the channel. My name is Dhruv. I am an engineer and CEO at Convolve AI Inc. At Convolve, we assist corporations, enterprises with their computer vision solutions, AI solutions. So if you are interested, you can get in touch with us. The contact information is in the description below. So in the last video, one of the previous videos, I specifically talked about differences between NeRFs and 3D Gaussian splatting, but I wanted to do a deep dive into NeRF because a lot of people want to know how this works. So hopefully this video will help you understand. I remember when I started learning about NeRFs, reading about NeRFs, it took me a very long time to understand, and there was some material out there on YouTube, but mostly it took me some time and a lot of discussions with peers to understand. So in this video, I'll try to break it down to very simple steps so that a beginner can understand. So this is a beginner's 101 for NeRFs. So before we actually begin, you can see NeRF method was introduced by UC Berkeley, Google Research, and San Diego, UC San Diego. And here is a demo for the one of the scenes where you can see the camera moving around and you can see the nice rendering as well as the depth map on this side. All right, so guys, this is another illustration. So these objects have been trained using NeRF, and then you can render 360 views. You can move up and down, and from all different angles, you can get such beautiful rendering. For computer vision, this is really good, and this has been learned just from images, and hence that's the reason this particular technology was particularly revolutionary in the field of computer vision. All right, now what is the overview? Overview is basically the most important thing to understand first is that NeRF is learning one single scene. So you are optimizing for one single scene, you are fitting your neural network to learn one single scene. So a lot of people when talking about neural networks talk about generalization to new domains. NeRF is not meant to do that. The idea here is about generalizing to novel viewpoints rather than new domains. So the idea is for a scene, for example, this is the scene. You have a set of drums. You have input images, and these images are taken from different viewpoints. So here you can see the camera is taking images from multiple different viewpoints. Let me add a pointer here. So here you can see the camera, and that is taking images from multiple different viewpoints, and once you have those images from different viewpoints along with the position, the pose of the camera from which that image was taken, you optimize a NeRF. So this is a NeRF that you optimize, and out comes a trained NeRF which can be queried to produce these kind of novel views. So here you are rendering new views. So that is the idea. Once we go forward, we'll see the input into the neural network. So this is basically a NeRF. This network here is represented as a NeRF. The input is position XYZ. So this, think of it as a 3D location in space. So you have, say, so for your scene, you have this cuboid or a cuboid of a scene. And in there, for this particular point, you have an X, Y, Z, and theta and phi. Theta and phi define the viewing direction of that particular position So XYZ is the Cartesian coordinate for that particular point in the 3D scene, and theta and phi defines the viewing direction, viewing angle. So that means from what angle is your camera looking at. XYZ defines the spatial information, and theta and phi help in reflectance. So depending on what angle your camera is looking at the scene from, the reflectance properties would change. Okay, so if you have ever taken pictures from different angles, or when you look at different objects from different viewpoints, different angles, you will see different kind of reflection. So that's what theta and phi define here. All this is fed into this network, and outcomes for that particular point are GB, so that's the color, and sigma, which is called the density. So this is the output. Once you have that output, then you do a process called volume rendering. Volume rendering we'll talk about in the slides to come, but think of it as an integration. So basically, for a camera image, for this image, for example, what you're doing is, every camera, the way a camera captures an image is, for that particular image, for every 3D point in the scene, light rays will fall on the optical center of the camera, right? So the way a camera would work is that, or way your eyes work is, right, each point in 3D world is emitting light, and the light rays coming towards the sensor of the camera, or in terms of your eyes, into your eyes, right? So those rays are coming into the camera and are essentially forming this image. So this is the image plane, and when a ray hits this image plane, that's what you define as a pixel, right? So now for each optical center of the camera, there are different rays that are thrown out of the optical center into the world, okay, and each ray will define basically a pixel in the image, right? Now for each ray, the idea is to sample points, and once you've sampled points, you will pass it through this neural network to get RGB for each point, and then you do volume rendering, which is like an integration to integrate the input of each of these points to get the final value of that pixel. So that is in a nutshell what NeRF is doing. So going into the depth about volume rendering, as I said, think of it as integrating the input from different points. How it's integrated? Well, you need to have a sigma, which is a probability of a ray terminating at that particular location. So essentially, if sigma is very high, that means you have hit an opaque thing. So for example, here if you see this peak of sigma's peak, essentially showcases that you have hit a big object here, right? So throughout the scene, the sigma is low, and when it's high, possibly it is high where your ray has hit a part of this excavator, for example. So that's the probability of ray terminating. And if your ray is hitting an opaque or a highly translucent object, the probability of it terminating goes to a very high extent. That means the light would not travel any further, and your sigma will go up. It becomes high. O plus TD ray, R is the camera ray, so this is the origin of the camera, and TD is the D is the direction, and T is the different intervals at which you are sampling. And this is the entire equation of volume rendering. It's kind of a lot of math, but you can think of it in a simple way. This function C is essentially defining color for each point, sigma is defining the importance of that point, and T is kind of defining the accumulated transmittance, that is how much of energy is left in that particular ray. And when you integrate everything, you get the final color. So this equation is used to integrate all these points to get the final color at that pixel. Now this is volume rendering. In a computer setting, you have to do volume rendering through numerical quadrature, right? Because well, you can't do integrals in computers, so you break it down and accordingly you do this kind of volume rendering using using discrete samples, right? That's all this slide is. Now if we move forward, there are a few tricks to get NeRF to work. Now what are these tricks, and what we can do about these? The most important thing is that essentially there is a trick in NeRF called positional encoding. The idea behind positional encoding is that when we are feeding, if you go back to this first slide, when we are feeding x, y, z, theta and phi into the network, this is very limited information to predict this, right? So what happens is mostly these networks, fully connected deep networks, they are biased to learn low frequency faster. So they will learn low frequency features in that particular image. Low frequency means overall structure of the image will be learned, but high frequency features are not learned. High frequencies are, for example, in this image of the line, you see the hair, the plants at the back, everything with regards to the eyes and fine details. Those are called high frequency features. So what positional encoding is, this is taken as an inspiration from transformer model. It's able to do better, and here you can see this lion has done much better. And similarly, if you look at this curve here, right, with regards to the PSNR, with the better positional encoding, the PSNR is signal to noise ratio, which improves a lot, which is a metric to see how good your rendered image is. It improves a lot. Okay. Second trick is hierarchical sampling. So basically, as we defined, so if I draw this out, in terms of the NeRF, you have a camera, right, and a ray is sent out, and on the ray you sample points, right? So the idea is that how do you sample these points, right? Well, the first step in NeRF is to just do normal coarse sampling. So it's kind of a uniform sampling, like you see here, stratified sampling, and you add a little bit of perturbation to it just to add a little bit of variety. Using that coarse sampling, you train a coarse network, and that learns some representation of the scene, and then you take the outputs from the coarse network to adjust the sampling of the fine network. So then there is another network that, instead of doing this kind of uniform based sampling, it does a more informed sampling, and that information comes from training of this coarse model, and that would do higher sampling, for example, around areas where there are objects, so the volume density is high, and very few samples where volume density is low. That way your model is able to get more detail around the areas where there are objects, where the density is high, and you don't really care about empty spaces, so that's where you don't spend much time, and that's where the fine network comes into play. And then the computation of the final is using fine plus coarse. So here's how you do the get the information about the fine sampling. Well, from the coarse samples you can make a distribution, you can create a distribution of your weights, and then using that you can get like a measure for fine sampling and use those fine samples to further compute your output RGB, and that's what is called hierarchical sampling. Alright, so guys, next comes the structure. The network is very simple. It's not a CNN, it's not a transformer, it's just an MLP, fully connected neutral network. And here you can see the input. So now input actually is X, Y, Z, theta and phi, right? But and in this case, when you in the first stage of the network is just X, Y and Z, but you see that it's written 60 here, right? It's said that it's 60 dimensional. The reason is this 3 dimension is mapped into 60 dimensional vector using positional encoding. So you add this, put it to 256, 256, 256. So this is the size of the hidden layers. And then over here, you again add XYZ with positional encoding, just to add information about the 3D space position of your of the input that you are giving to the network. And out comes the volume density here. That's one of the outputs. And here you give it the positional encoding of redirection, which is basically the viewing angle, theta and phi of the camera. And from there, further, it's able to compute the RGB. So this viewing direction, which is theta and phi, they do not impact the volume density, but they impact the color. They impact the reflections. So that's why at this stage the volume density is already predicted, and at that point positional encoded camera redirection is fed to get the final emitted color. Okay, so now from an implementation standpoint, the first step is to get poses of the camera. Either you have ground truth poses through some measure, maybe you have really accurate poses in the data set, maybe you already have RTK GPS to get your camera poses. In most cases, most of the methods use cold map. This is a structure from motion technique. The idea behind cold map is it's a complicated method, but the idea is that you have a camera going around in the scene, it does feature matching, and then it tries to optimize the pose of the camera, and it gives you it calculates the pose for you. So it's like a pose optimization problem that it solves. Now the second step is you optimize neural networks that represent volume representation for every scene, and the loss to do that is this, very simple. It's RGB loss. In the preliminary NeRF work, the only loss that was used was RGB. Going forth, there have been papers who have used RGB loss, LiDAR loss, depth loss, and numerous other loss terms have been added to this equation, but at the core is RGB. So using the RGB of your predicted image and the RGB of the input image, and you're comparing that, and you're comparing the output of the coarse network and fine network, and that is your loss. So loss is pretty simple in this case. So again, the idea is like if you go back to this initial image, the idea is that for that particular camera input, you are, for example, for this particular camera input, you have the ground truth image. You tell your network to predict the image after doing prediction and volume rendering, and then you compare it with the ground truth. So you have original ground truth RGB, you have predicted RGB. All you're doing is comparing the two, and you are producing your loss, and you're back propagating that through the network to get your final output. So that is the implementation part. And again, the examples we showed, this is what you get. So the paper overall is very nice, and there are a lot of follow-up works. And recently, again, as I talked in one of the previous videos, Gaussian splatting, which is the use case is same, but it's totally different concept. NeRF is good because not only does it give you these amazing renderings, but also if we go back to the first slide here, it also gives you depth, right? So if you look at this, this is a depth map, right? So it has inherently, just by RGB, learned the depth of the scene as well. So this is really powerful. It has been used for urban reconstruction of scenes. Google has done a lot of work, Block NeRF, urban Radiance Fields. Then Wabi has done a lot of work. This has revolutionized the self-driving car industry. There is NeRF-based methods to simulate LiDAR, to simulate driving scenarios. Wabi has a paper called Unisim, which is really nice. So there's a lot of amazing content out there. So next in the video, we will make a video, or I plan to make a video to look at the code to understand how the code for NeRF works. Guys, if there is any preference you have in terms of a paper to review or to discuss, kindly leave that in the comments, and we'd be happy to go over that. That's it for today, guys. I hope you like this video. If you like the video, please hit the like button, subscribe to the channel, and hit the bell icon so you are notified about any new video that we upload. We will be uploading a lot of content about computer vision, AI, and hopefully about language modeling as well. So please stay tuned. Share this with a friend if you find this useful, because that's a good way to help others and also to help our channel. Thank you very much, guys, and I'll see you in the next video.